Hello everyone. So in today's class, we're going to discuss about the one of the important reactions, Sharpless asymmetric oxidation. Before that, let me explain the key of yesterday's assignments. So yesterday's discussion was on Bayer vinegar oxidation, where acids were used for the conversion of carbonyl into the esters. Okay. So the migratory tendency will be generally tertiary alkyl groups will be highest, then followed by the secondary, then phenyl, then methyl. Okay. So the as per the migrating tendency, phenyl will be going to get more migrating tendency. So oxygen insertion will be going to happen here. Okay. So it is going to substitute for phenyl ester. Okay. Now this is secondary and this is tertiary. Okay, so tertiary will be more migrating, so oxygen insertion will be going to happen at in this position. Okay, so if it is hydrogen and phenyl will be going to get more migrating tendency, so oxygen insertion will be here. Okay, now for the olefin and peracid combination, so it's going to be epoxide formation. That epoxide is also selective. Okay, so selective in terms of the electron rich systems. So the double bond which is more substituted will be more electron rich, more nucleophilic, so that epoxide formation will be going to happen to this double bond, resulting into the product which is similar to this. Okay, so this double bond which is less substituted will not be epoxidized because it is less electron rich when compared to this. Okay, now in this condition tertiary potassium is from the not above side. Okay, but it will not give any steric hindrance. Okay, if it is below side it's going to give steric hindrance. Okay, so attacking of the epoxide from the above side is going to happen. So the following epoxide will be formed. So the final product will be this. Okay, and this is unsaturation here, which is going to react with peracid. Okay, to result into the epoxide. So don't think that it is not a CC double bond which will not react. So any unsaturation can be epoxidized with the usage of the peracids. Okay, so here one more combination with carbonyl. So if this is the case, this is a tertiary. Okay, and this is secondary. So tertiary will be going to oxidize, so oxygen insertion will be here, so resulting into a 7-membered system. Okay, so these are the products that are formed with the Bayer vinegar oxidation. Okay, I hope all the students have done this. Okay, so doing assignments will make you perfect, so try to make as much as assignments and as much as questions to be exposed. Okay, so next topic, usage of the peracids. So these are very similar reagents which are much similar activity with per acids. In the peracid also you are going to find oxygen peroxide bond, whereas in peroxide also it will be same oxygen single bond, peroxide bond will be formed. In peracids with the oxygen single bond, peroxide bond, along with there will be a carbonyl. Okay, if it is not carbonyl and if it is like elements, then it is said to be peroxide. Okay, this is a hydrogen peroxide. Okay, hydrogen peroxide. If it is a system like this is a tertiary butyl and this is hydrogen. So it is tertiary butyl hydrogen peroxide. In short form, it can be called as TBHP. Okay, tertiary butyl hydrogen peroxide. These are the well-known peroxides that we are going to use for the oxidations of the olefins. Okay, so then what is the difference between hydrogen peroxide and per acid reactivity? Okay, if it is a MCPPA, this is MCPPA, and this is a hydrogen peroxide. If these two are present, then if any conjugated systems, okay, let's suppose I need to oxidize this double bond, okay, epoxidize this double bond, it is a conjugated one. So if this is the condition, as the nucleophility of the conjugated double bond is less because it is involving in the conjugation, so per acids will not be much efficient to epoxidize conjugated double bonds. In that condition, hydrogen peroxide is the best reagent which will convert the conjugated double bonds into the epoxides. Okay, so do remember, if it is conjugated system, H2O2 will be the best reagent. If it is non-conjugated, MCPPA will be the best reagent. So if non-conjugated, can we use H2O2? Of course, you can use H2O2 for non-conjugated systems also. But if it is conjugated system, you must use H2O2 because its reactivity is more when compared to acids. Okay. And one more thing, usage of the peroxides for the epoxidation. Usage of the peroxide for epoxidation is needs the support of the metal alkoxides. Okay, metal alkoxide support will be needed for the usage of the hydrogen peroxides. Okay, so we going to use generally combination of metal alkoxide with TBHP, tertiary butyl hydrogen peroxide. This is the one of the example which converts the allylic alcohols, okay, allylic alcohols into the epoxy alcohol. Okay, so allylic alcohols oxidation, epoxidation. Okay, so what is the role of metal oxide? So metal is going to make a bridge between the hydrogen peroxide, whatever may be the hydroperoxide. Okay, so it's going to form a bond as this is a metal alkoxide. So let's suppose I have taken metal hydroxide, okay, or metal estate. So this is not going to involve. So metal is going to join, okay, in an attractive manner, and as well as it is going to bind with the oxygen of the alcohol. Now exchange of the oxygen to the epoxide is going to happen. Okay, exchange of the oxygen to the epoxide is going to happen. So this is what the transition state that going to generate. Here metal is facilitating the epoxide formation by the donation of the peroxide oxygen, okay, to the olefin. So without metal, that's why this linkage will not be possible. That's why it will be less efficient to epoxidize without metals. Okay, so with this the product resulting product will be stereochemically diverted into the similar or one type of products. Let's say if you see next example, you are going to understand. So during the epoxidation of this, we are using the metal. So metal is going to bind with the same side where alcohol is present. So alcohol is above the plane. So metal is going to bind to the same plane, and oxygen of the peroxide will also bind to the same side. Now delivery of the oxygen to the olefin will also be same side. So resulting the epoxide, which is a similar stereochemistry to the hydroxy. Okay, so whenever you are using metals are going to bind to the hydroxy, resulting into the epoxide into the cis fashion, whichever the already alcohol is present, the same side epoxidation will be going to happen. Okay, so this is one more example which elucidating the epoxide formation which is in a same direction or same stereochemistry as alcohol. So this is a hydroxy from above side, and to the same above side epoxidation is going to happen. This will be the major product of this reagent. Okay. So after many advances, we have seen the titanium silica supported hydrogen peroxide combination is less efficient. Okay, is more efficient when compared to vanadium and molybdenum. Okay, so now most of the questions are based on titanium silica based hydrogen peroxide treatment. If ever you are encountered with vanadium oxide and silica in presence of TBHP, that is also hydrogen epoxidizing reagents. Okay, so these are three combination of the epoxidation reagents. Okay, so mostly titanium is going to use for the epoxidation. So these are the example for the titanium epoxidation. So where double bond is going to epoxidize. Okay, so if it is methyl downside, epoxide will be above side. Okay, so for methyl groups, stereochemistry will be opposite. For any conjugated system, like say this is oxygen. Okay, so oxygen is going to facilitate the titanium attack, as well as it's going to facilitate the delivery of the oxygen. Okay, so resulting into the epoxide, which is conjugated. Okay, so for conjugated we need to use hydrogen peroxide, which are more efficient when compared to for acids. Okay, conjugated systems you need to use peroxides. Okay, mostly hydrogen peroxide. So this is one more example with the H2O2. Okay, so here this is allylic alcohol which is going to epoxidate. Okay, so allylic alcohol epoxidation is very famous if it is asymmetric. Okay, so next we are going to see the asymmetric allylic epoxidation. So before that we will see unsaturated carbonyl compounds epoxidation. Okay, so as we discussed, this is one of the example. H2O2 is used for the conjugated olefins to facilitate more epoxidation. Okay, so this is one of the example with hydrogen peroxide for the conjugated carbonyl system to get conjugated epoxide. Okay, so one more example. This is a progesterone enzyme. Okay, so with the usage of hydrogen peroxide in presence of basic condition, so this is a non-conjugated, this is non-conjugated, and this is conjugated. So with the hydrogen peroxide usage, conjugated are more reactive when compared to non-conjugated. So be careful. So it has a selectivity of conjugation. So conjugated will be more reactive when compared to non-conjugated. So only conjugated olefins will be going to epoxidize. Okay. Now, so asymmetric epoxidation. This is one of the very important topic because it is used very extensively for the allylic epoxidation. Okay, so this is what allylic double bond, which is present of alcohol. So here titanium is the metal which is going to facilitate the epoxidation, and tetrabutyl hydrogen peroxide is the oxygen donor. Okay, so the thing is usage of plus L diethyl tartarate. Tartaric acid is this. So this is what mesotartaric acid. If it is substituted with ethyl, this is what diethyl tartarate. This diethyl tartarate, if it is not meso, okay, let's say this is present, active diethyl tartarate is present. So it can be in the two forms, either plus or minus, based on the optical rotation. Okay, so if it is in plus condition, it will support the epoxidation into the above the plane when the arrangement of allylic alcohol in this fashion. Okay, so be careful and be attentive. If the olefin is present and alcohol, the allylic alcohol is down and right side, right down, then if you use plus diethyl tartarate, it's going to be above the plane. Okay, if I use plus diethyl tartarate, it will be epoxide will be the above the plane. Okay, and if the same orientation is present and if I use minus diethyl tartarate, then epoxidation will be below the plane. It is very important and most probably expecting question. Okay, so the orientation of epoxidation will be governed by the diethyl tartarate. Why it is going to govern this? So it is going to facilitate the epoxide oxygen delivery of the tertiary butyl hydrogen peroxide. So these three, diethyl tartarate, titanium tetraisopropoxide and tertiary butyl hydrogen peroxide, three together are going to form a transition state. Okay, this transition state will be going to facilitate or will be going to direct the stereochemistry. Okay, let's say this hydroxy group is present in this way. Okay, now what could be the product? Let's say if this is a condition, you must compare. So what is the relation between these two? If I rotate this into 90 degrees, okay, 90 degrees, so the double bond will be going to happen this. Okay, so what is the relation between these two? So these are enantiomers. Okay, are very similar but mirror images. Okay, so if I use this with plus diethyl tartarate and titanium tetraisopropoxide and tertiary butyl hydrogen peroxide, is going to give, this is called beta or above the plane, beta hydroxy group. Okay, and this is used with the diethyl tartarate minus, so it has given alpha. Okay, alpha. Now its enantiomer will be in opposite way. So if I use plus diethyl tartarate, okay, plus diethyl tartarate, it will be going to give alpha epoxide, and if it is minus diethyl tartarate, it will be going to give beta epoxide. So it will be changed based on the orientation of the double bond and alcohol group. Okay, so whatever may be the molecule, you must compare with these two orientations. Okay, now whatever the double bond is similar to condition 1. Okay, this is the double bond which is similar to condition 1. Okay, so if the condition 1 is similar, so with the plus diethyl tartarate, beta epoxide will be formed, minus diethyl tartarate, alpha epoxide will be formed. Okay, so let me explain with one more example. So look at here. So this is the orientation. If I rotate this with 90 degrees, so this is in the orientation of like this, which is enantiomer of earlier product. Okay, earlier combination. So if this is the condition with the plus diethyl tartarate, it will be alpha epoxidation. Okay, and minus diethyl tartarate, beta epoxidation, isn't it? So this is similar to this. Okay, so whether hydroxy is down or hydroxy is above, it is not going to change. Okay, but this orientation is going to change. Here what is the connection of the alcohol, that going to change. So in this condition, if it is plus diethyl tartarate, it will be going to give plus alpha. Okay, if it is minus, so it will be beta. So be careful. If you not understand, repeat once again, so that you can understand the mnemonics. This is called mnemonics or stereochemistry governance. Okay, so how it is alpha, how it is beta. Okay, so mechanism is not required, because mechanism will be going to make you overwhelmed. So I'm not involving in the mechanism, but you need to adapt the orientation of the allylic alcohol. Okay, if it is oriented with this form, okay, where double bond is attached to the alcohol, to the downside, okay, and down right side, okay, where if it is a double bond arranged vertically, okay, so then plus DET will be going to give alpha epoxide, and minus DET diethyl tartarate will be going to be beta epoxide. In the same condition, if the double bond is oriented in vertical and alcohol is to the down left side, okay, down left side, then it will be reverse of this condition. If it is plus diethyl tartarate, it will be beta epoxide, and minus diethyl tartarate will be alpha epoxide. Okay, so this is very important. So Sharpless asymmetric epoxidation, so most expected questions. Okay, now after this you need to work out with give an example. So let's try assignments for today. So the first one, asymmetric epoxidation of Sharpless will be going to happen with only allylic alcohols. Okay, only allylic alcohols. So I'm using titanium tetra isopropoxide and TBHB and plus diethyl tartarate, and others. Then what could be the product? Next, similar with minus diethyl tartarate. So these all are same. What could be the product? Okay. Next. So in the first condition, it is plus diethyl tartarate. What could be the product? With along with titanium tetraisopropoxide and TBHB. And next fourth one, it is minus diethyl tartarate. Then what could be the condition? Okay. Next, fifth one. Using plus DET plus Sharpless conditions. Okay, what could be the product? Next, minus DET and Sharpless condition. So write all the products and send by the WhatsApp. Okay, thank you.